Ah. 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 Okay. Okay, let's see. Today. Huh. Oh, it's time. Okay, let's get started. All right. So, we are in the middle of, learning about normal subgroups and quotient groups. And this week, where is everyone? I don't know. Oh, there's two of you. That's 40% of the class. Speaking of percentages, seems like some of you had some rough time with the exam. Make sure you understand why you missed problems you missed. Every one of them can be explained easily using just the concept of normal subgroup. So keep practicing, keep refining your understanding of the concept of normality. All right, so what we're going to talk about now are some more refined facts about quotients in particular. That's the first thing I'll do today. I'll tell you the main theorem of quotient groups, so to speak. Then I'll do some thing that we might call index mathematics. How do indexes of groups work? One group in another. And finally, I'll state some goals, some short-term goals that we're building towards. And if you want to read, the relevant places to read that will align most with what I'll say in class are in chapter 10 and 11-ish. All right, somewhere in there. Read both. Why not? Okay. All right, so let's begin with number one. Every image is a quotient. That's an interesting. That's interesting sentence. So let's talk about this. This is the most fundamental fact about quotient groups. It's called the first isomorphism theorem, I think. Some people call it the first isomorphism theorem. All right, so what is it? What's the context? You have a group homomorphism. All right, that's the That's the context. And what is the statement? The statement is this. Theorem. The image, let me say it like this. There is a natural isomorphism of G mod the kernel with the image. Alright, so the image of any homomorphism, quote, is a quotient. That's why I said it like that. i.e., images are quotients. Meaning, isomorphic to. Alright, so every time you see a group, and every time a group is mapped to another group by homomorphism, its image is simply one of its quotients as an abstract group. Alright, so this is the content of the theorem, but I'm going to spell it out even more precisely. More precisely. So we're given this homomorphism. Okay? You can also draw another homomorphism in the same picture. You can draw the quotient map, which is always available. The kernel is a normal subgroup, so Gmod that is a group. This is a group because kernels are normal. Quotient group. Alright? And the statement is the following. The theorem is actually that there exists a unique map homomorphism P bar. There exists a unique P bar such that the diagram commutes, making the composition of the two arrows equal to the top arrow. i.e., Q composed with phi bar is the original phi, i.e. this. Composition holds. Furthermore, phi bar is an isomorphism onto its image, which is equal to the image of phi. So this is the actual first isomorphism theorem. This is also okay. So what it's saying is that the way we say this colloquially, you might hear an algebraist or a mathematician say it like this. The homomorphism, this is just language, factors through the quotient. Factors through is used as terminology because if you look at this condition, it's like one map was like written as a product, but composition. Yeah, it's like Q times some other map. So it's factor through means your given homomorphism goes intermediate, passes through a quotient map. All right, so quotients are, in other words, quotients are sort of like, are the gatekeepers of homomorphisms out of the group. Alright, so how does the first isomorphism theorem get proven? The proof of the first isomorphism theorem is rather silly. Okay, so the proof, I'm going to prove this statement. The proof that G mod the kernel is isomorphic to the image is very easy. Okay, so let's go through it. So the first step one, we will construct a homomorphism from G mod the kernel to the image. Which I'm gonna call phi bar, because it's gonna be the one that's in the more refined statement of the first isomorphism theorem. So I'm gonna write phi bar for this. It's gonna be a map from this quotient to the image. Okay? Here's the definition of phi bar. Phi bar of a coset. That's a coset. Is phi of that element. Now there's a huge warning here. Immediately when someone defines such a thing, there is an issue. The issue is whether this is a function at all. That's the issue. So notice, stare at this. You send this left coset to the original homomorphism, output it at this single element x. Now the issue is this well-defined? Meaning, let me write out the condition of checking well-defined. Meaning, if one coset happens to be another, except you've witnessed it using different representatives, x and y, two different people in the same country, representing the same coset, if these two are the same, why should phi bar of this equal phi bar of that? It better. Otherwise, you have not defined even a function. It is not single valued. It doesn't obey the vertical line test. Whatever you want to think of as not being a function. All right, so we need to verify this. Let's check it. Suppose x times this coset, suppose phi bar of this equals phi bar of that. Meaning, phi of x equals phi of y. Sorry, no, that's not right. Not right. Sorry, I'm being dumb. Suppose two cosets are equal. I read the wrong line. Suppose two cosets are equal. Apologies. Okay, suppose you have two cosets represented in two different ways. Then that means that y inverse x is in the group, is in the kernel. I'm just using this. AH equals BH if and only if B inverse A is in H. This little left coset fact. Okay, so that's this. But then, by definition, that means that phi of y inverse x equals the identity in the target group. Okay. But then homomorphism says homomorphism property, and you can get there, and you get here. So then, in other words, if you represent the same coset in two different ways, phi of one representative is still the same as phi of the other. And therefore, this recipe is well defined. You come back tomorrow and you represent the same country with a different representative, phi of that representative and phi of yesterday's is the same element in the target group. Yeah, well defined and injective, exactly. Okay, so so we confused those, but I fixed it. All right. Okay, so this is well defined. You have to check whenever someone defines a map out of a quotient by first choosing a representative and then doing something to that representative and saying this is the output. You always have to check whether that's a well-defined map. It could just be garbage. Okay? That's something to be aware of. Okay. So this is a well-defined function. Why is it a homomorphism? It's being a homomorphism is obvious. You know. I mean, the group structure on the quotient group is by definition this. I'm just going to multiply this out. This is by definition, by construction, this coset. This is the rule of phi bar, and this is phi of x times phi of y. Etc. Good. Very good. Good. Okay. So there you go. It's a group homomorphism from the quotient to the image of phi. Of course, it's to the image of phi because look at all the outputs. The outputs are outputs. The outputs are outputs, folks. So there you go. This is a homomorphism. Step 2. Prove that phi bar is injective and surjective. Okay, so you go and do that. So injective. So actually surjective, obvious. Surjective is very easy. Suppose you have some element in the image. Of the original homomorphism. Then, i.e., g prime is phi of some x. Then, by the rule, phi bar of x's coset equals g prime. Done. Okay, there you go. Surjective, injective. Suppose quotient map. Phi bar of some coset equals the trivial element. Then, by definition of phi bar, because this is equal. This is equal. That's the definition of phi bar. And the definition makes sense because we checked, it's well defined. Then phi of x is this element. That's what it's saying. The top line is saying this. i.e., x is in the kernel. But then the coset is the trivial coset, which is the identity element of the quotient. There. So the kernel of the phi bar map is simply the identity element in the quotient group. So kernel of phi bar is just the identity element. Done. Injective, surjective. So phi bar is an isomorphism from the quotient to the image. All right, so every time you see an image under a homomorphism, you are simply looking at Gmod the kernel as an abstract group. As up to isomorphism, you are looking at Gmod the kernel. So that's great. Okay, someone redeemed, Mr. Know-It-All redeemed Twisted Cubic. So there you go. Here's your Twisted Cubic, Mr. Know-It-All. Although you already know about it, so that's fine. Okay, great. So let me show you a consequence, for example. Consequence. Just one of many. All right, here's the consequence. If G is a finite group, and you have a homomorphism to another group, then the size of the kernel times the size of the image is the size of the group. Now, some of you might have seen something. This might seem like some analog of some other phenomenon that you saw somewhere else. This should ring a bell. This should look like something you learned, some story in linear algebra, some linear algebra involving rank and nullity. Some kind of general algebraic conspiracy might be explaining all of these. I don't know, maybe there should be a subject that goes and explains it all as really one sort of principle manifesting in many different ways. I don't know, that's just a suggestion. Sorry, Shirshak, you're absolutely right. I should do that. But see, guys, it's a multiplicative version of the additive thing in linear algebra that you learned, rank nullity. Okay, so kernel size times image size is size of the original group. That's good to know. In fact, you shouldn't just memorize that. You should memorize, if anything, that the image is isomorphic to the quotient group. So you should think of it as this. That's how you should think about it. Okay, good. Good. So that's our first isomorphism theorem. Every image happens to be a quotient. The quotients are all the images, folks. And now think of, okay, let me do another consequence. Let me just do another consequence, all right? So another consequence. Or this is not really a consequence. This is not a consequence. This is just an observation. Just a quick observation that if G is simple, then phi of G is either trivial or the same size as G, isomorphic to G. it's in that sense that the simple groups are atomic. They don't collapse before being placed inside of another group. They can't in any intermediate sense. Any homomorphism out of a simple group either injects the group in, or it just annihilates the whole group and throws it away. All right, so simple groups are the atomic groups. They don't get intermediately squashed. They don't factor through a quotient, an intermediate quotient. All right, let's do some index math now. Let's discuss indexes for a bit. Let's discuss index. Okay, so what's the context here? Whenever you have H, a subgroup. Not normal, doesn't have to, nothing, just a subgroup. Then I want to recall for you that the index is the number of left cosets. It's the size of the set of left cosets. So please be aware, when we write G mod H, we are not saying that it's a group in general. We are simply writing a name for the set of left cosets. Okay, so this is just the number of left cosets, all right? Yeah, oh, if it's infinite, just put an infinity there, folks. And if it's finite, it happens to be this. We learned this, all right? This is how Lagrange's theorem is proven. Okay, so the index is just that. It's a measure of how distant the subgroup is away from being the whole group. The order of H, the size of H, is how big it is. Meaning how big H is. The index is how far away from the totality is the subgroup. They're related like that. They're complementary like that. Okay, so here's the question here's the thing I'm gonna establish. Suppose now you have a chain of subgroups. Is a chain of subgroups. No normality, nothing. Just 3 nested groups. Okay. Then how do the following 3 numbers Did I get them all? Yeah, how are they related? This is something I want to write out. Okay. So the relationship is something called it's called a Tower law. Relationship might be, some people might call it Tower law. Which is the following. That this one is the biggest, which makes sense. But it's equal to the product of the other 2. And I want to say something. This is an equality whenever all the 3 things are finite numbers. Because otherwise you're just gonna get infinity equals infinity. And so the places where this law is actually useful is when all 3 are finite numbers. So let's pretend that. Let's assume that that was the case. Okay? Good. Now you might say, isn't this obvious? Isn't this obvious? Obvious? Because after all, left-hand side is this divided by this. And the right hand side is and so everything cancels, so obvious. And when G is a finite group, when G is a finite group, then yes, this works. But it doesn't work if G is infinite. It doesn't work that way if G is infinite. But this argument doesn't work. And the statement is that it's always true whenever all three of these indices are finite. So that's why the Tower law is more interesting than it originally appears. It's for finite groups, it's just that fractions multiply like that. Things cancel. But for in arbitrary group theory, you have to do something else. So I'm gonna do something. I'm gonna sketch I'm gonna lay out the argument for how you prove something like this. So how to prove this Tower law. For groups. All right, step 1. Construct a function. It's just a function, so I'm going to call it f. From the set of these cosets, which is a finite set by assumption. To the other thing, to this one. This is also finite. Remember, we're in this setting. So let me construct this function for you. Let me give you the name of this function. Ready? I'm gonna feel a little bit. Okay, here we go. The function is f of a coset is by definition the same representative coset of H. Oh my god, but this is bad news. This is warning. Warning. Why is this even a function? Is it well defined? Is this even a function? Okay, let's check this out. If xk equals yk, if the same coset g mod k, g mod a, what's the assumption? It's just our assumption. Let's assume that there are finitely many elements in this set and in this set. Just let's assume that everything in all the indices are finite. And then we'll see that there's always a multiplicative conspiracy. Otherwise you're gonna get some like infinity equals infinity type statement, which is not as interesting. Yeah, so we're just pretending that that's the case. So this is a finite set, Sloth, and this is also a finite set. That we're pretending. Okay. But what I'm about to show you doesn't appeal to the finiteness. Just the fact that we have a function is super general. So this function is super available. Okay, so if x times k is y times k, then what? X inverse Y is an element in K. But then, since K is in H, X inverse Y is in H. But that means, in turn, that the coset of X for H is the same as the coset for Y. I'm using this simple fact about cosets that I wrote on the margin over here. Two cosets are the same if and only if this kind of element. It's a little simple tool. You use it all the time. Okay, so here it is again. If the same coset is written in two ways, look at the two different labels, X and Y. Look at the X inverse Y thing. It's in H. So therefore, XH is the same coset as YH. And this is this implies well-definedness. Because my map was, you take this, you read this thing, and you output that coset. But you'll always get the same coset. XH will equal YH as a coset if you swap X with another Y that keeps the same coset in the input. All right, so this is well-defined map. So now step 2. This map is surjective. So what is F? You take a K coset and you send it to take a representative and take the corresponding H coset. That's what the map is. So now I just have to take an H coset and show that it came from a K coset. All right, so suppose Z times H is an element in here. Any element. Where Z is an element in G. That's assumed. Then consider or take this coset of K and notice the following obvious fact. F of that coset is this, just by how F is defined. Done. F is surjective. Step 3. And step 3 is the hardest step. The goal is this. Show that the fibers, meaning, show that for any coset in the target set, the set F inverse, which simply means all the x's, all the elements in the domain, it's just inverse image, it's a pre-image. Show that this set is in bijection. Oh no. Remember when my thing freezes? Oh, good. That this set is in bijection with H mod K. All right, now step 3, I will assign as homework. Use the orbit stabilizer discussion. So refer back to the first time I mentioned orbit stabilizer. The way I proved it was I set up a bijection between G mod the stabilizer is in bijection with orbit. Okay, use that version, that refined version of orbit stabilizer. This left coset space is in bijection with the orbit when X acts on a set. All right, that's what we're going to use as a homework assignment to pin down this thing. And so if you accept this, then if you put it all together, so then the total number of elements in the domain is the total number of elements in the target times, for each element in the target, the number of elements in the domain that mapped to it was always a set of size h mod k. Follows. All right, so the Tower law is true whenever all three indices are finite. That's the point of this index math thing. And the proof for the general groups is trickier, but forces you to think about well-definedness of various maps. It helps you practice those skills. So that's why I wanted to show it to you. Okay, so this important part here is actually an incarnation of orbit stabilizer, which I'll assign in the homework. Okay. Or you don't have to wait for me to assign it. You can try to prove it yourself. Teacher's pet. Teacher's pet doesn't require any action. I just recognized. Okay, so crow is teacher's pet as is common, and so good job. Great, good for you. Okay, so now what I'm gonna do is end class with stating two short-term objectives. Okay, the first is much more important than the second. First is called the classification of finite abelian groups. In other words, we have a complete simple list of every single finite abelian group imaginable. That's a huge, important milestone in group theory that you need to, every student must understand. So that every finite abelian group, it's not a mystery what it is. It'll be a product of a bunch of cyclic groups. And when are two of these products the same? We will establish that. It's simple. It's not, meaning the end result is simple. Proving it is not. Okay, so classification of finite abelian groups. That's our first short-term objective. I'll try to finish this by office hours. In fact, I can almost guarantee it because office hours can go as long as I want. So classes plus office hours. We'll finish this. And the one thing I want you to pay attention to in the proof of this classification theorem is pay attention to the following use of quotient groups. Oftentimes they'll want to prove something about a finite group G, and then some math will happen and you'll end up talking about some normal subgroup will show up. Something happens, some math happens, and some normal subgroup shows up by some cleverness. Okay? And then the next move is often to pass to the quotient, which is a group that's smaller. And then you use induction on, you can use induction type arguments on the size of the group to sometimes prove the statement for your current group. So this is a common template for proofs in group theory, and the utility of the quotient group. It helps you sometimes, if you have the ability, it helps you deduce something about your group by induction on the size. So that's, and classification of finite abelian groups will use this trick at least once. Okay. So 2. Throw our entire bag of tricks. Throw, not through. At the following statement. The first, so actually there are 2. The first non-abelian simple group is A5, and B, there is only one simple group of order 60. Okay, this is B is going to be harder, and B will take more time, unless I can come up with a better way to do it. This will take more time. But this, we have lots of tricks now to sort of get rid of all the orders up until 60. So we will see, 45. Okay, 45. If a group has size 45, look, it had a non-trivial normal subgroup. Out. Oh, if a group has order, it's abelian. Oh, this is dihedral. This is okay. So, etc. Throw all the bags until you see that at 60, 60, obviously you do have a simple group, but then the question is it the only one? And it is by very difficult mathematics. Okay, make the Cayley table, right? 60 by 60, and then chase it. So 3,600 entries. You know, every row has, everything appears only once in every row and every column. Magic square. Go for it. Yeah, no luck. Hey, Burrows. Hey, what's going on, Dr. Burrows? Oh, yeah. Heading off to class, you're teaching some kind of chemistry, I noticed. I can never tell which kind it is, but it looked fancy. Oh, shout out. Shout out. You want to learn chemistry of all kinds? Go check out Dr. Burrows' stream. And anime. If you're interested in anime, like if you're a little bit too interested in anime, go check out Dr. Burrows. Okay. Make the Cayley table in office hours. Good. Yeah. That would be a good use of office hours. Maybe the students will actually show up for office hours that way. I'm not sure. Actually, no, that the opposite will happen. Even negative students will show up for the office hours. So that's, I guess I'll skip on that. Good. So review what we did today, students, and see if you can do step 3 before I write out the homework and tell you the hint. I'm gonna spell out an even bigger hint than this one. So see if you can try your hand at step 3 on your own. Okay, so with that, I do have to go because I have to eat and come up with what to say from my calculus student. I know, Tropical Geek, you do. Tropical Geek, you didn't... Is today... I don't know. Just in case, Tropical Geek, this is your usual Sungite infusement. Totally experimental, by the way. But, no, Tropical Geek is not. Tropical Geek is just a random person out in the wild. Just like you, bro. Alright, but you're a teacher's pet, so, yeah. Okay. Anyway, more on this. So classification of finite abelian groups is a huge, great result. And let's just see, let's try to witness how A5 is somehow a first little gem in group theory. That it's the first simple group that's not Z mod PZ. That's silly. Okay, that's what we're building towards, and I'll see you next time in abstract algebra. Okay, let me do this. Let me do this for once. Anthropology class? Isn't anthropology either like super boring or like incredibly interesting? Depends on like how BSy the professor is. But it can get really interesting. Like you're learning about all kinds of different people and cultures and stuff. That could get fascinating if it's taught right. Wait, wait. Cannibals? That's amazing. How is that not interesting? That's fascinating. Yeah. Oh, okay. Yeah, see, yeah, that's what I mean. It could either become a disaster. It's very, very professor dependent, I feel. I guess everything is, but all right, bye. Yeah, see ya. Yeah, good talk, pro. Yeah, see ya.